solutions to the Chapter 12 homework, which a lot of people didn't do. So this first one was just a center of mass problem. So that's a formula that's on your formula sheet. You simply sum up the mass times the position at all the points, divide by the sum of all the masses. You can get that. So for the y-axis, that's vertical, I have A, B, C, and D. Sorry, I didn't do them in order. I accidentally was thinking x-axis first, but I used 8 instead of 10 centimeters, so that's the y-axis. At any rate, add all those up, so vertically speaking, and then you divide by the sum of the masses, you get the average location of mass vertically is at 5 centimeters. For the x-axis, I did them in order, A, B, C, and D. So multiplied that A and B by 0 centimeters because they're right along 0 centimeters along the x-axis. C, D multiplied by 10 centimeters because that's how far away they are from the origin on the x-axis, divided by the total mass, which is still 800 grams as it was up here. So I get a position for the center of mass of 6.25 centimeters, I think, or 6.3 centimeters, I don't know, horizontally, and up 5 centimeters vertically. So to find the moment of inertia in this case, it said imagine that you had a vertical rod or a rod coming out of the page going through A, and this whole thing was rotating around A. So essentially I'm taking B, C, and D as point sources at different distances. So B is 200 grams at 8 centimeters or 0.08 meters. C is 300 grams and it's at this distance, which I had to use Pythagorean theorem to find. So that's 0.128 meters. And then this is D is 0.1 meters away and it's 200 grams. So this is a bunch of MR squareds. That's a formula on your formula sheet also. Add all those up, I get the total moment of inertia is 0.0082 kilograms. For problem 18, this is asking about the net torque. So you've got a 30 Newton torque force acting clockwise, a 20 Newton force acting counterclockwise on this, radius of 0.02 meters. I said a 4 centimeter diameter. So essentially, this is causing a clockwise torque. This is causing a counterclockwise torque. The net torque is the difference between those. So it's 0.2 Newton meters clockwise. This is a graph of torque versus time. So think of this essentially similar to force versus time in linear land. And so the area of a force time graph would be impulse. So this is essentially angular impulse. So what you're asked here is you say you have an initial angular velocity of 0.25 radians per second. You have a moment of inertia of 4 kilogram meters squared. And then essentially, if this graph shows the torque applied in the time, what would the final angular velocity be? So you have a positive torque over time. The area of that is going to equal 20 Newton meter seconds. So essentially the initial angular momentum is 4 kilogram meters squared times 0.25 radians per second. And then I add this, which is the area of the graph, and that gets me my final angular momentum, which is 3 is it Newton meter seconds, I guess? I don't know. Kilogram meters squared per second, I guess, is another way to think about that. But that equals the moment of inertia times the final angular velocity. So 3 divided by 4, that gives me a final angular velocity of 0.75 radians per second. So like I said, if we're thinking force time graph, that should be easy to understand that that's impulse. So this is angular impulse. For problem 32 here, this was asking, you had a cat here, you had tuna fish here, you had cat number 1 here, saying where can cat number 2 be to balance this thing? And the fulcrum is in the middle of a 4 meter long plank. So 2 meters to the end of this on the left, 2 meters to the end of that on the right. So I'm thinking torque clockwise is equal to torque counterclockwise. Force of cat 1 times the distance of cat 1 equals force of tuna times the distance of tuna plus force of cat 2 times distance of cat 2. So do all that, and I can find out the distance of cat 2 would have to be 1.5 meters to the left of the pivot point. That should have been quite an easy problem. For problem 33, it's basically, I think I'll look at this. Open it up the book. So it says a car tire is 60 centimeters in diameter. The car is traveling at a speed of 20 meters per second. What's the tire's angular velocity? So we just take linear velocity divided by radius, 66.7 radians per second. If it wants it in RPM, so we get that at angular velocity in radians per second, 1 revolution over 2 pi radians, 60 seconds over 1 minute. This is essentially unit conversions like you learned way back in chemistry land. So therefore, the speed at the top is twice the average speed. The speed at the bottom is 0. Because the instant it's touching the ground, it is not moving. Problem 44 had something rotating here. 2 meter long rod at 120 RPM. Gave the mass of the rod as 0.5 kilograms, or maybe 500 grams, I don't know. And it's asking what's the angular momentum vector of the bar. So give your unit, answering unit vectors, which is a little annoying. That's the I hat, J hat, K hat thing we talked about early in the year. So essentially I multiply this through, I get that it's going 12.57 radians per second, or basically 4 pi radians per second. So moment of inertia of the rod about a center is 1/12 ml squared. That L is the total length. So I get 0.1667, which I think is 1/6 of a kilogram meter squared when rotating about the center. So the angular momentum is those two multiplied together. It's around 2.09 kilogram meter squared per second. So if you use the right-hand rule, curve around, your fingers going counterclockwise, your thumb would point out of the page toward you. So that's how we figure out the direction. Problem 59 is basically another torque problem. So you've got someone sitting out there 4 meters from the end. You've got a beam here, which is 6 meters long, and you've got a cable hooked at the end of the beam at a 30-degree angle from the beam. So the key here is finding out the tension in the cable. So this is a torque problem, because if it's a torque problem, we have balanced torques and balanced forces. I'm choosing my fulcrum as the wall, because the wall has a force acting on this, similar to an example I did in class, but it is an unknown force. So if we put the fulcrum there, then we can ignore it when solving this problem. So I'm going to have torque counterclockwise equals torque clockwise. The mass of the beam is 1,450 kilograms. The mass of the person is 80 kilograms. Multiply both of those by 9.8 to get their weights in newtons. So here, the counterclockwise torque is caused only by the cable. So that's the tension in the cable multiplied by its connection point, which is 6 meters away, multiplied by the vertical component of the force, which is sine of 30 degrees. So sine of 30 degrees is 0.5 times 6 is equal to 3. So I get tension times 3. On this side, I have the weight of the beam, 14,210 newtons. It is at its center of mass, which is 3 meters from the wall. And then the person is 4 meters from the wall. So I get around 45,766 newton meters of torque. Clockwise, that would have to equal the counterclockwise torque, so I'm dividing by the distance that I have over here. So I get that the tension in that cable would be 15,255 newtons. That wouldn't be the vertical component of tension, that's the actual tension in the cable, which if you're in construction, that's what you're interested in, because there's limits and braking limits and things like that. Problem 71 is a problem where we're looking at something that's not rotated about the center, so it's a parallel axis theorem. So you have a 5 kilogram object. It's 0.3 meters in 60 centimeters in diameter, so 0.3 meters in radius. The axle's going here and it's rotating about that. So essentially, what you're being asked to do here is figure out the initial angular acceleration and figure out the angular velocity when it's directly below. So this is going voom below. It's basically falling down due to a gravitational torque. So the first thing I'm going to do to get angular acceleration, I got to get the torque and I got to get the moment of inertia. So the moment of inertia is the moment of inertia about the center of mass plus the extra due to the fact that it's not rotating about the center. That's the parallel axis theorem. So for a solid disk, this is 1/2 mr squared. And the extra caused by it not rotating about the center is md squared. So 0.5, 5 kilograms of mass, 0.3 meters squared, plus this 5 kilograms of mass times 0.3 meters squared away. That gets me 0.675 kilogram meters squared is my moment of inertia. The torque is going to equal to the fact that the weight of this thing is acting down over here. And it's the initial torque when this is acting basically perpendicular to the axle. The torque will decrease as it swings down because the effective distance from the axle decreases. But it was asking for the initial torque and the initial angular acceleration. So mg, 5 kilograms times 9.8 newtons per kilogram is 49 newtons, and that's acting 0.3 meters away from the axle. So that's 14.7 newton meters of torque. So the angular acceleration is simply Newton's second law for rotation around 22 radians per second squared. Now this one is asking what the angular velocity is here at the bottom. There's a couple ways you could solve this. The easiest one is conservation of energy. So up at the top here, we've got gravitational potential energy that decreases as it goes below, and it would decrease by 0.3 meters because that's how far the center of mass falls. So the initial kinetic energy is 0. The initial gravitational energy is this, 49 times 0.3, so somewhere around 14.7, I think, joules of energy. And then at the end, we're going to say that's our zero height, so there's no gravitational potential energy at the end, but there is rotational kinetic energy, 1/2 I omega final squared. Well, we know our I, and we're trying to find our omega final squared. So this might have thought about solving different ways, but this is, I believe, the easiest way. The last one is a similar one to an example I did in class, so that's problem 86. So essentially you're asking to find, you've got a 2 kilogram block here, a 4 kilogram block here, a solid disc is a pulley with a mass of 2 kilograms, a radius of 0.06 meters, and essentially what you're doing is, and there's 0.5 newton meters of friction. It sounds very complicated. You're asking to find the time for this 4 kilogram block to hit the floor 1 meter below. So my method is turn everything into linear land, because essentially I need to find the acceleration of this system. So if the 0.5 newton meters of torque caused by friction is acting at the edge, I could say that that 0.5 newton meters is equal to the frictional force multiplied by the distance of 0.06 meters. So I could say that's equivalent to 8.33 newtons of force acting on the edge. So now if I want to find acceleration, I can say net force over mass equivalent, not mass total, mass equivalent. 4 kilograms times 9.8 newtons per kilogram would be the essentially force causing acceleration on this side. Forces on this side are 2 kilograms times 9.8 newtons per kilogram, and then 8.33 newtons equivalent caused by friction. We subtract both of those off from the force on this side. The total mass of the system is 8 kilograms, but the equivalent mass is 4 kilograms for this, 2 kilograms for this, and this pulley, because it's a solid disc, has an equivalent mass of 1 kilogram. Why? Because the average location of mass is acting as if it is 1/2 the way out. That's what the 0.5 mr squared means. So I could essentially say this is acting like a 7 kilogram system. That gets me an acceleration of 1.61 meters per second squared, and now I can simply use delta y equals 1/2 at squared to figure out the time to fall. Method 2, so I did this 2 different ways. Mine's sort of a cheat code way, but might be a little less obvious to an AP reader. Method 2 is torques. Well, here I get 4 times 9.8 times 0.06 meters is my counterclockwise torque. This is a clockwise torque caused by the 2 kilogram object. So I'd subtract those off, and also subtract off the 0.5 newton meters of torque due to friction. So overall, that's the amount of clockwise torque with friction and torque caused by the 2 kilogram mass, and this is the counterclockwise torque. So I get a net torque of 0.676 newton meters clockwise. To find the angular acceleration, I take that torque and I divide it by the moment of inertia. Well, what is the moment of inertia? Well, it's essentially this 0.5 mr squared. So 0.5 times 2 kilograms times 0.06 squared. But these two things, which are not on the circle, but they're acting like they are, these two things act as if they're completely on the outside. So they are basically mr squareds. So 4 kilograms at 0.06, 2 kilograms at 0.06. So it's since they're at the outer edge. So essentially I get that torque divided by all that moment of inertia. That gives me this angular acceleration. I can use this conversion, we've talked about this for a long time now, since first semester, to go from angular acceleration to linear acceleration. So essentially, if I want to get linear acceleration, I take this and multiply it by the radius. And lo and behold, I get the same linear acceleration as I did before, so I get the same time to fall as I did before up here. So a couple different ways to solve that. Hope those help. For people who didn't try them, you need a look.